Okay, great. Yeah, thanks for the introduction. And there is a slight shift of the talk. So unfortunately, I think Alan Shane won't speak before me. That's I actually originally planned that there will be a few people talking ahead of me about some common slides. So I may repeat a little bit. So you might heard I think 5 talks about QFI and well you might think that entanglement, quantum entanglement is QFI, but it's not. I will talk about a little bit more than QFI, about some different entanglement for fermion systems with indistinguishable degrees of freedom. So so in a solid state, when we talk about entanglement, it comes from the challenge that we do not have the access to wave functions. So we cannot do identical wave function measurement, and we cannot do site-related, site-dependent measurement of entanglement. So in the end, we have to indicate entanglement from some available measurements. Actually, back in 30 years ago, when people measure alphas in strongly correlated material, it has been known that if you can, if you have a well-screened semiconductor, a metal system, you can use alphas to reproduce basically everything. Like Robert just mentioned, you can use alphas to reconstruct neutron scattering, reconstruct optical conductivity. You can for a low entangled or no entangled system, you can do that for basically everything. And if you see this, that's an indication of no entanglement or low entangled system. But for strongly correlated system, usually what you will see is you cannot do this repetition. If you have an entangled state and you measure the alphas and measure neutron scattering, there's almost no relation. You need a lot of vertex correction to reproduce one from the other. You cannot just reproduce by autocorrelation. Right. So this is a kind of very early version of the indication of using spectral to indicate their entangled state in this material. So the question I want to answer is, well, can we use the difference of the spectral as the indication of entanglement and going beyond the quantum Fisher information? So since Alan won't talk before me, I will want to give a very brief recap about spin QFI. It is, as Matteo and Robert just mentioned, it is a fluctuation of the spin degrees of freedom defined at each individual local site. So for any multipartite spin entangled state, it has a well-defined bound. The bound is below 4 times k times s squared. K is what Matteo and Robert called M, the entanglement depth of the spin system. So it connects the quantum metrology, the so-called Cramer-Robb bound, the uncertainty of a unitary measurement to the solid state spectroscopy, because the integral of solid spectroscopy, a subtract of the elastic peak, gives us the entanglement. So this is a nice experiment done by Alan Shea and Alan Tennant using 1D corporate chain, and they found that if you measure neutron scattering by cooling the temperature, you can reproduce what the MRG gives us as the QFI, and you can witness the 4-particle entanglement. Okay, so if we want to generalize this concept, this notion to general materials, we know that spin is not magnetic material is not the only quantum material what we talk about. There are correlated metals, there are charge density waves, there are all different kind of material. And entanglement is actually a fundamental property of the wave function, and we just chose our operators to witness them. And the spin QFI may not serve as a good operator to witness them. So when we generalize from a spin system, we have to think about what's the best operator we should think about. And actually, for the spin system, when we define the QFI, we just talk about the modes. We have well-defined spin modes. We have an electron sitting at the site 1. the spin sitting at side one is forever side one. It's just flip the spin. Right? So you can define the modes by the psi one, psi two, phi one, phi two, and you have the cross product about them. So that's our the notion we use to define the spin entanglements. They are naturally separated because of the modes. But when we define the electrons, when we generalize to general electron problem, we have to take into account the fact that electrons are not defined by modes. Electrons are indistinguishable particles. So you do not have the well-defined, we have electron sitting here or there. There's electron modes, and there are just the n number of electron modes. They have the anti-symmetric symmetry. So the electron wave function has to obey the anti-symmetric relation, and the 2.2 electron wave function is never the product of the two electrons. Of the two functions. So actually they are stator determinant. When you have many electrons, you will have many of these determinant anti-symmetry terms. So this gives us some ambiguity when we define entanglement based on modes. If we still use our modes, this super exchange will enter our calculation, and they seems to indicate all electron systems have entanglement, but that's exactly not what we want to call entanglement. Right? So we have to find a way that not indicate entanglement just for this anti-symmetry. And this has been done by I mean, not very recent, but 3 years ago by Philip Hall paper. So instead of using the product of wave function, we can use the product of a block of fermionic operators. And this is not separable block of fermionic operators. So this will avoid you defining the entanglement, just counting the antisymmetry of fermions. But this is not the end of the story, because as Robert mentioned, we can actually have the entanglement based on different definition of bases. You can have a Fermi C, and the Fermi C may be transformed into real space. You will tend to call it entangled. But this is not a trivial way of defining entanglement because we do not want to classify everything, all the Fermi C, to be quantum materials, right? So the nature of a fermion, the indistinguishable nature of fermion, tells us it's also ambiguity of the choice of orbital. The orbital, the basis we use to define our fermions are just our human thoughts. Right? There's no natural orbitals in real space. When we say d orbital, s orbital, they are just our definition of the spherical harmonical wave functions. We just use them as a basis. And electron wave functions are there, and there's no natural definition of orbital. So we should define a way that avoid the ambiguity of orbital. So we should insert we should allow the system to transform by any unitary transformations of orbital. So you can transform by different ways, and you get maybe different partitions of the fermions, and you take the minimal way to define the entanglement. So that means for anything that transforms from a Fermi C, it becomes a Fermi C in the end. So in the end, we have to allow the unitary transformation. It has to be a quantity defined against a unitary transformation. So we generalize the wave function into not only the product of fermionic block operators, but we also allow a Gaussian transformation on top of it. This Gaussian transformation can traverse all the matrix, all the unitary matrices. So this allows the fermions to transform in any definitional basis. So based on all these bases, we find the minimal value of the maximal block. That's our way to avoid all these ambiguities in electrons. Another thing we have to take into account is that, this is the unitary transformation we talk about. So for any Gaussian transformation, you will get exactly the same, you will get the unitary transformation of the orbital, like e to the I psi, which is psi is the Gaussian matrix. So another thing we have to take into account is the fermion can have a different fitting than the spin system. When we see a fitting of the fermion system, we are talking about a fitting based on our human-defined orbital set. Actually, if you're working on quantum chemistry, you know that even for hydrogen molecule, you need about 10 orbital to precisely calculate it. So orbital is also, again, a mathematical tool. It's not the real existing concept. So instead of counting the maximum orbital in each block, we should count the maximum number of particles in each block. Because orbital you can define arbitrary number of orbital. Right. If you take a pair of right. Yeah. Yeah, exactly. So if you allow any unitary transformations, you should become a Fermi C in the end. That's what I'm talking about. So when we talk about fermions, we have to avoid classifying those states that are identical to Fermi C. So this is an example I want to show that for this example I used in the cartoon. We assume we have only four different basis choice by unitary transformations. From the first choice, we have the entanglement depth being 3. The second from second one we get 2. From the fourth one we find the maximum block, we get 4, and from the last one we get 3. And we have to find the minimal value for all the bases that gives us a 2. So the entire wave function, when we see a fermion wave function, we do not see any bases. Right? This gives us the entanglement depth being 2. So based on this notion, we can define our fermion entanglement witness. So the idea is if we have the K-producible fermionic state, we can find a quantity which satisfy all these conditions, and that requires us to have the operator, a choice of a fermionic operator, which is resilient to the fermionic's intrinsic antisymmetry. It shouldn't classify antisymmetry as entanglement. It's also invariant under any unitary basis rotation. We can when we transform, we do not get a different value, and it's also monotonic with the entanglement depth or the multi-party entanglement K. So it's better to be linear, but not necessary to be linear, but it has to be monotonic. And it's also measurable by solid state. These are the 4 criteria we are looking for the electronic entanglement characterization. So the property we focus on is the 2-particle reduced density matrix, the 2-RDM. It's defined as a 4 fermion operators. It's called 2-particle, but it's actually, when we say 2-particle, that means 2 pairs of electron hole. So it's an OIJKL defined by CI, CK dagger, CL dagger. That's a measurement of any 4-particle response, any 2-particle response. So if you think about the KL equal to IJ, you initially recover the spin or charge response, which was discussed in the quantum Fisher information concept. And if we think about the classical counterpart of it, the weak theorem, the decomposition, you can subtract the classical part, the 2-particle, the 2 fermion or single particle terms out of these 4 fermion terms. That becomes the cumulate 2-RDM or 2C-RDM. So this 2C-RDM naturally gives you one-ish result, 0 result for Fermi C, for Slater determinant. So you can see that because you satisfy the weak theorem, for any Fermi C, you will get 0. Right? And it's also, it's not invariant under unitary transformation, but it's unitary under unitary transformation. When you have a unitary basis transformation, you have a unitary transformation of this tensor, of this the 4 tensor. Right? So that means if you can calculate the singular value decomposition of the tensor, you get the invariant of the unitary transformation. But yeah, it's very difficult to calculate the for tensor the singular value. We did that, but it's difficult to build a series. So we choose a compromise, which is a flattened matrix of the tensor. We group two pairs of the indices, and we calculate the singular value of the eigenvalue of the matrix. Because this is also part of the tensor's transformation, so they can verify this matrix is also unitary under the unitary transformation. So the eigenvalues are also invariant. Okay, we satisfy the two conditions we want. Now we have to think about whether the entanglement depth will really increase when we the measurement increase with the entanglement depth k. So there's one important property of QRDM, which is the separability. If we have these blocks of the block partition of a wave function, these two particle, the 2C RDM can be decomposed according to these partitions. So there will be any overlap, will not be any overlap. So you can perfectly decompose by these different partitions. And that also means the eigenvalue of the matrix is also a maximum. The maximum eigenvalue is a maximum over all these blocks. Right? So you can have a linear relation to pass the block eigenvalue to these entire eigenvalues. So as long as we can find the upper bound or supreme of the block eigenvalue, then we know that what's the bound for our 2C RDM entanglement depth. Entanglement witness. So let's try to calculate what's the upper bound for this maximal eigenvalue in our flattened 2C RDM. And for two producible states, this has been well studied in 20 years ago by quantum information people, especially by Ignacio Cirac. Any two-particle wave function, or two-particle wave function can be decomposed according to the so-called Slater decomposition. You can so this is a general way of writing any two-particle two producible wave function. But you can decompose by a unitary transformation into a diagonal form, a block diagonal form by only two pairs of electrons per block. This is proved theorem in quantum information. And using this general form, we can minimize, we can calculate the maximal value of the lambda max by varying all this zi, zj. So we can choose all different r. R is the stator rank with the sum of these blocks. Well, we are not, right? So two-particle RDM is just the operator expectation value. Yeah. Oh, yeah, so that's a very nice question. So theoretically, we want to find the supreme, and that gives us a guidance when we do measurement. If we find some, if we get some value which is above the supreme of a given K producible state, that means we have to be K plus one producible state, because we already traversed all possible K producible state when we prove it. Right. For K reproducible wave function, we calculate supreme. So the supreme for all n producible wave function is called mu n. And of course, for infinite producible wave function, you get infinity. For any value we want to prove this is monotonic with n. Mu n is always monotonic with n. And as long as we traverse all possibility, then in experiment, if we get something, we know where it is in terms of all these bounds.
we could discuss afterwards. When you do experiments, you don't have a luxury of doing an inference to make a basis. You're working whatever basis you're given.
Well, experimentally, you do not have basis. You just choose, you measure the RDM, and this is the basis invariant thing. Okay, we can chat offline. Yeah. So for two producible state, we can mathematically prove the maximal eigenvalue is 3. It's 3/4, and the minimal is something that we won't need in the end. So we actually did a numerical simulation. We found, okay, there are statistical distributions of all randomly chosen two producible state, and is indeed bounded by this value. I have to speed up for a three producible state. We do not have a luxury to we do not have the stator decomposition anymore, so we cannot traverse all possibility. But we talk about two usually called maximally entangled state, the GHZ state, which is an analog of the stator decomposition in the two producible state, and we found that the maximum bound is it's a 5/4, and we also talk about the W state, which is another type of maximal entangled state in quantum information, and the maximum it's an analog of a spin state actually. The maximal eigenvalue is also 5/4. So that means for a three producible state, although we didn't traverse all the possibility, but for those maximum widely believe the maximal entangled state, the bound is 5/4. And we can generalize to a k-producible state, and what we get is a half times k minus a half. This is also a conclusion known from the GHZ state, not the R rank GHZ state, but rank 2 GHZ state in quantum information. Okay, so the conclusion tells us that this upper bound, we can also generalize to mixed state, but this will not change the conclusion. The upper bound mu k increased linearly with the entanglement depth k. So it's also it's linear and it's monotonic. Right? So that means we can use this upper bound to classify this block of wave functions, and it gives us the entanglement depth. This is a simple numerical experiment for some quantum information state. The spin 3, GHZ3, we get the upper bound up to the theoretical value. And when we go to a larger system, we can get the upper bound exactly matching our theoretical derivation by numerical sampling the state. Okay, so we have satisfied 3 components. The last component we have to satisfy is the 2C RDM has to be measurable by spectroscopy. I do not have time, so I have to move a little bit faster. So we talk about RIGS in the previous talks. And the RIGS is assumed to be a excitation of the local atom. You have the X-ray and you have a particle hole excitation, and after some lifetime, the particle hole excitation will drop back. So you do not, usually you do not assume that the core level hole will move between different atoms. But this is actually not true. I mean, or for any core level, you have the bandwidth. So if we assume that core level electron can move, you can actually show using perturbation theory that you will get the 2C RDM. You will get the 2 RDM, not the cumulated, the 2 RDM, part of the 2 RDM using this core level perturbation expansion. And this expansion is not just a theoretical expansion. This has a specific momentum pattern, which you can use the Fourier transform of 2 momentum to extract this pattern. And we did the simulation of the RIGS spectrum, and that gives us the multi-point correlation, the 4-point fermion correlation, which matches, I mean, not 100% correct, because we numerically calculated the spectrum and we take the finite energy window, but you have a good match with the result. So using the 2C RDM, we can 2 RDM, we can subtract it from APAS. And we get the 2C RDM. This disconnected part can be measured by APAS. And again, RIGS didn't measure all parameters, and RIGS only measured the leading parameters or leading hopping terms. So this is a 2C RDM we simulated from Hubbard model, that the size of the dots indicates the value of the matrix elements. And this matrix tells us what can be measured by RIGS. And of course, neutron scattering can also be measured by RIXS. And if we overlap them, we found that, okay, RIXS didn't measure all of them, but measured the most important of them. So RIXS gave us a good estimation for all these 2C RDMs. And then we can apply this strategy. We have this last point being checked that we can measure by spectroscopy. We can apply this spectroscopy to some physical experimental relevant models. For example, we measure the extended Hubbard model in the doped case, which is no longer a spin dominant case. We have almost a metallic situation. And we found that in the exact 2C RDM, you get these values, and the RIXS gave us not precisely match, but you have the same order of magnitude that gives us the same classification of the k-partite entangled state. We get the two-partite state. But if you use QFI, you will see that QFI cannot be able to witness any entanglement because this is no longer a spin dominant state. Again, we also apply to another, which seems to be spin dominant state, a 2D triangular lattice Hubbard model at half filling at the candidate of a spin liquid. We found that, okay, if you measure the eigenvalue of the 2C RDM, you get you have a maximum at the quantum spin liquid phase, and you also have finite value at the metallic phase. So you get, if you measure RIXS, you get almost a perfect match with the exact values. But if you do the QFI measurement, you get almost the exact value. You get the consistency with 2C RDM for spin liquid and dimer phase. But for the metallic phase, the correlated metallic phase, you will lose the entanglement. But actually in 2C RDM, you still capture the entanglement in the metallic phase. So this is in contrast to the entanglement entropy. For entanglement entropy, because it only used the local information to characterize entanglement for the small u for the metallic phase, it actually diverges. It makes the DMRT simulation really hard. But actually, if we consider the fact that it's a metallic phase, we should allow the non-local transformation to classify it. Okay, so I already run out of time. I want to give a quick summary that we talk about the multi-party entanglement for electron system, the criteria it has to satisfy, and how to measure it using APAS and RIXS, and how to apply it in correlated systems. So I want to collaborate. I want to acknowledge the collaborators. It's a visiting scholar in my group, Tongtong Liu, and my postdoc, Dogen Xu, and also students, 2 students. Thanks for, and also the funding agency from DOE.
Thanks very much, Yao. While we switch, yeah, question, please.
I'm wondering if this is similar to the particle entanglement spectrum that is finding rapid Hall state.
Right, it's related, but it's not exactly the same because we have to consider all these unitary transformations.
Thank you. You want to report? Okay.
Right.
Thank you.
Right, it's related. It's a two-party RDM is a concept already used also in the quantum chemistry and also quantum information used to identify. It's just that we derive the bounds of this.